The morning of November 14th, 1942, Richmond, California. Shipyard number 3. A welder named Joseph Scullion stands at the bow section of hull 467, staring at a problem that shouldn't exist. The steel plate before him, 3/4 of an inch thick, 12 feet long, has warped. Again. The 4th time this week. The riveting crew that attached the previous section had done everything by the book, following specifications handed down from the Navy Bureau of Ships in Washington. But the book was wrong. Scullion ran his gloved hand along the buckled seam. In the cold morning air, he could feel the stress in the metal itself, the invisible tension where hot rivets had punched through cold steel, where thermal expansion had fought contraction, where the fundamental physics of shipbuilding were pushing back against an impossible deadline. 328 feet away, at the stern of the same unfinished hull, another welder was discovering the same problem, and in the adjacent slip, hull 468 sat incomplete, waiting for a riveting crew that wouldn't arrive for another 6 hours because the night shift had walked off, exhausted. And beyond that, 17 more LST hulls in various states of construction, each one a monument to the same brutal mathematics. The United States Navy needed 1,050 landing ships to invade Europe, and at the current pace of construction, they would have perhaps 200 by the summer of 1944. The invasion would fail before it began. Not from German guns, not from Atlantic storms, but from the simple, crushing reality that America couldn't build ships fast enough to transport its own army across the English Channel. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Joseph Scullion was 43 years old that November morning. He had come to Richmond from Pennsylvania's steel country, from a lifetime of welding bridges across the Allegheny River, water towers in Pittsburgh, and once briefly, before the Depression ended the project, the structural supports for what would have been the tallest building west of New York. He understood metal the way a musician understands an instrument. He knew that steel had memory, that it remembered every stress, every temperature change, every moment of violence done to it, and he knew that the Navy's specifications were killing their own ships before they ever touched water. The landing ship, tank LST in the brutal efficiency of military acronym, was not elegant. It was not fast. It was, by every aesthetic standard, an ugly vessel. 328 feet of flat-bottomed, blunt-nosed utility, a steel box designed to ram itself onto hostile beaches, drop its bow doors, and vomit forth 20 Sherman tanks or 163 fully equipped soldiers or 2,100 tons of ammunition, gasoline, rations, medical supplies, and all the material sinew of amphibious warfare. The British had invented the concept in 1940. The Americans had refined the design in 1941. By 1942, every strategic planner in the Allied command understood the same calculus. Whoever controlled the production of LSTs would determine when and if the Western Front could be opened. Adolf Hitler understood this too. German intelligence reports from that autumn noted with satisfaction that American shipyards were hopelessly behind schedule. The Kriegsmarine calculated that at current construction rates, the Allies couldn't possibly mount a cross-channel invasion before 1945, perhaps 1946. By then, the Atlantic Wall would be impregnable. By then, new U-boat designs would make supply lines impossible. By then, the war might already be won. They were almost right. The problem was elegant in its simplicity. Traditional shipbuilding took too long. An LST hull required 300,000 rivets. Each rivet had to be heated to orange-white incandescence, carried to the hull while still glowing, driven through pre-drilled holes in overlapping steel plates, and hammered flat before it cooled. A skilled 4-man riveting crew, a heater, a catcher, a bucker-up, and a driver could place perhaps 400 rivets in a 10-hour shift if conditions were perfect. Conditions were never perfect. Rain stopped riveting work entirely. Wind scattered heat. Night shifts required massive lighting installations that drained power from other parts of the yard. And most critically, there simply weren't enough skilled riveters. The craft required years of apprenticeship, A feel for the work that couldn't be taught in the 6-week training courses that Kaiser's shipyards were running for new workers, flooding in from farms and factories across the country. The Navy's answer was to rivet anyway. Slower was acceptable. Delay was acceptable. What was not acceptable, what the Bureau of Ships had stated explicitly in Technical Bulletin 7-4, dated June 1942, was the use of welding on critical structural seams of combat vessels. Welding was faster, yes. A competent welder could seal 30 feet of seam in the time it took a riveting crew to place a few dozen rivets. But welded ships cracked. The heat of the welding torch, 3600 degrees Fahrenheit at the tip of the flame, transformed the crystalline structure of the steel itself. As the metal cooled, internal stresses built like a coiled spring. Welded seams could fail catastrophically, splitting open under the stress of rough seas or the concussion of nearby explosions. The Navy had learned this lesson in World War I, when welded merchant ships had literally broken in half in the Atlantic. They had reinforced the lesson in 1941, when a welded destroyer escort developed stress fractures during sea trials and had to be scrapped. No welding on combat hulls. It was doctrine, backed by 30 years of maritime engineering experience. Joseph Scullion thought the doctrine was going to lose the war. He had been watching the problem build for weeks. Hulls that took 8 weeks to rivet when the yard first opened in January were now taking 10 weeks, 12 weeks, as the workforce expanded faster than training could keep pace. Quality control inspectors were rejecting entire sections of hull plating because rivets had been improperly set, because steel had been improperly aligned, because exhausted workers on their 14th consecutive 12-hour shift had made inevitable mistakes. And the deadline kept approaching. Supreme Headquarters Allied Expeditionary Force. Eisenhower's command needed the LSTs by spring of 1944, not for D-Day itself, which was still being planned, but for the invasion of Sicily and then Italy, the campaigns that would draw German divisions south, away from the French coast. Without LSTs, there would be no Sicily. Without Sicily, there would be no Italy. Without Italy, there would be no D-Day. The entire strategic architecture of winning the European war rested on the question of whether American shipyards could produce enough of these ugly utilitarian vessels. Scullion walked away from Hull 467 and headed toward the yard supervisor's office. His hands were still shaking slightly, not from cold, but from a calculation he had been running in his head for 3 days, checking and rechecking because the answer seemed impossible. The supervisor that morning was a man named Dutch Hendricks, 57 years old, a former merchant marine captain who had traded the bridge of a ship for a desk job coordinating the chaos of wartime production. Hendricks was drinking coffee from a thermos, reviewing production reports that were universally bad. Every yard in Richmond was behind schedule. Yard 3, Scullion's yard, was the worst of them all. Scullion knocked on the open door frame. "Mr. Hendricks, I need to show you something." What Scullion showed him was a section of scrap steel, roughly 2 feet by 3 feet, with 3 different types of seams. The first was riveted, standard Navy specification. The second was welded in the conventional manner, a continuous bead running the length of the seam. The third was welded differently. Instead of one continuous line, the weld had been applied in sections. 6 inches here, skip a foot, 6 inches there. A pattern that looked random but wasn't. "I stress-tested all 3, Scullion said. "Used a hydraulic press in the metallurgy shed. The riveted seam failed at 8,000 pounds per square inch. The continuous weld failed at 9,000. But this one, he tapped the patterned weld, went to 14,000 before the steel itself tore. Not the weld, the base metal." Hendricks picked up the steel sample, running his thumb over the welded sections. "Why?" "Heat distribution," Scullion said. "When you weld continuously, you're pumping heat into the metal faster than it can dissipate. The steel expands, warps, builds up internal stress, but if you weld in sections and let each section cool before you move to the next, the thermal expansion stays localized. The stress dissipates. The crystalline structure stays stable. The Navy banned this. The Navy banned continuous welding because it fails. They never tested this. Hendricks set down the steel sample and picked up his coffee. He was quiet for a long moment, staring at production schedules that showed hull 467 wouldn't be completed until February, hull 468 not until March, the entire year's quota receding further into impossibility with each passing week. "If you're wrong," Hendricks said finally, "and one of these ships breaks apart in the Atlantic with 200 men aboard, that's on both of us." "If I'm right," Scullion said, "we can cut construction time by 60%. Hendricks looked at him. 60%. Minimum. Probably more. The mathematics were staggering. 60% faster meant an 8-week hull could be completed in 3 weeks. It meant the 200 LSTs that Richmond was projected to build by summer could become 500. It meant the impossible deadline might become merely difficult. It also meant bypassing Navy protocol, contradicting Bureau of Ships directives, and gambling men's lives on the intuition of a Pennsylvania welder who had never designed a ship in his life. "Give me 72 hours, Hendricks said. "Don't talk to anyone else about this. I need to make some calls." The calls went higher than either man expected. Hendricks contacted his immediate superior at Kaiser's central office in Oakland. That man contacted Henry J. Kaiser himself, the industrialist who had promised President Roosevelt that American shipyards could mass-produce vessels the way Detroit mass-produced automobiles. Kaiser had been looking for exactly this kind of innovation, this kind of radical rethinking of established practice. Within 48 hours, Kaiser's own engineers were at Yard 3, watching Scullion demonstrate his technique. They brought testing equipment, stress gauges, metallurgical analysis tools. They cut sections from Scullion's sample welds and examined them under microscopes. They subjected the welds to freeze-thaw cycles, to simulated storm conditions, to vibration tests that replicated the pounding an LST would take driving up onto a beach. The welds held. More than held, they performed better than riveted seams in every measurable category except one: fire resistance. A welded seam, if subjected to sustained flame, would fail faster than rivets. But LSTs weren't designed to survive fires. They were designed to beach themselves, unload, and get out. Speed mattered more than endurance. Kaiser took the results to Washington on November 23, 1942. Not to the Navy Bureau of Ships, which would have rejected the proposal out of institutional caution. Kaiser went directly to the War Production Board, the civilian agency Roosevelt had created to coordinate industrial mobilization. He brought data, test results, and a simple argument: we can build the ships you need, or we can follow regulations. Choose one. The War Production Board chose ships. On December 1, 1942, Kaiser's shipyards received authorization to implement experimental welding protocols on LST construction, subject to intensive quality control and ongoing Navy inspection. Joseph Scullion became, overnight, the most important welder in America. His technique, what the engineers called segmented thermal application welding, what the workers simply called skip welding, had to be taught to thousands of workers across multiple yards. Training programs had to be redesigned. Quality control inspectors had to learn new standards. The entire infrastructure of American shipbuilding had to adapt to a method that had been officially forbidden 3 weeks earlier. The resistance was immediate and fierce. Navy inspectors, who had spent careers enforcing riveting standards, now had to certify welds they had been trained to reject. Senior shipwrights, men who had been building vessels since before the First World War, watched as their craft was supplanted by a faster, younger workforce with welding torches instead of rivet hammers. Some of the opposition was professional pride. Some were legitimate concerns about safety. Some was the simple human resistance to rapid change in the middle of a crisis. But the production numbers were undeniable. The first LST, built primarily with skip welding hull 492, laid down on December 7th. 1942 was completed and in the water by January 9th, 1943. 33 days, keel to launch. The previous record had been 57 days. By February, Richmond Yard 3 was launching an LST every 3 weeks. By March, every 2 weeks. The technique spread to other Kaiser yards, to shipyards on the East Coast, to government-run facilities in Norfolk and New Orleans. The United States Navy, which had entered 1943 expecting to receive perhaps 300 LSTs by year's end, instead took delivery of 670. The invasion of Sicily, Operation Husky, launched on July 10, 1943, carried by a fleet that included 157 LSTs. The invasion of Italy at Salerno, 2 months later, used 108. Without Scullion's welding technique, neither operation would have been possible on the schedule that Allied planners had set. But the real test, the operation that would justify or condemn every shortcut, every innovation, every gamble taken in the name of speed, was still being planned for the spring of 1944, a single day when the entire material output of American industry would concentrate on 50 miles of French coastline. The spring of 1944 arrived with the weight of inevitability. Across southern England, in ports and harbours and temporary anchorages carved from agricultural land, the greatest amphibious force in history assembled itself. Portsmouth, Southampton, Portland, Dartmouth. Hundreds of thousands of men, tens of thousands of vehicles, mountains of supplies that required new units of measurement because the old ones, tons, trainloads, shiploads, had become inadequate, and among them, waiting in the grey Atlantic waters, were 236 LSTs, each one a product of the revolution that Joseph Scullion had begun, each one welded, not riveted. Each one carried the same question that had haunted Navy inspectors and Kaiser's engineers and Scullion himself through 18 months of unprecedented production. Would they hold? The answer came on June 6, 1944. LST 326 hit Omaha Beach at 6:47 in the morning, the fourth vessel in the first wave. Lieutenant Commander James Thompson on the bridge, watching German artillery find the range, watching the water around his ship churn white with machine gun fire. The beach was chaotic burning vehicles, dead men in the surf, smoke so thick it turned morning into twilight. Thompson drove his ship straight into it. Full throttle until the flat bottom scraped sand, until the bow was as far up the beach as physics would allow. "Drop the doors," he ordered. The bow doors, massive steel clamshell structures that formed the entire front of the vessel, were welded. Skip-welded, specifically, the seams applied in the pattern that Scullion had demonstrated on a scrap of test metal 2 years earlier. As hydraulic rams pushed the doors open, German artillery bracketed the ship. A shell hit 50 yards to port. Another hit the water directly ahead, sending a column of spray over the bow. The doors opened completely. 20 Sherman tanks, engines already running, began rolling down the ramp into 4 feet of water. Thompson counted them out. 1, 2, 5, 10, 15. All 20 away, churning toward the beach, toward the sea wall, toward the German positions that were turning the sand into an abattoir. Another shell hit, closer this time. The concussion rang through the entire hull, a sound like being inside a struck bell. Thompson felt it through the deck plates, through the steel bones of his ship. He waited for the sound he had been warned about, the high-pitched shriek of metal tearing, the rush of water that would mean a welded seam had failed. It didn't come. LST 326 backed off the beach at 7:03, 16 minutes after landing. The ship made 6 more runs that day, carrying ammunition inland, carrying wounded soldiers back to hospital ships waiting offshore. Each time, German artillery found the range. Each time, shrapnel tore through the life. Superstructure punched holes in the deck, shredded the thin plating of the upper works. The welded seams held, all of them, every single one. Across 5 beaches, Utah, Omaha, Gold, Juneau, Sword, the same story repeated. LSTs drove themselves onto sand and shingle, absorbed punishment that would have sunk conventional cargo ships, opened their bow doors, and disgorged the materials of invasion. Tanks, trucks, artillery pieces, bulldozers, medical units, signal corps equipment, aviation fuel, ammunition by the thousands of tons. By the end of June 6th, 132,000 troops had crossed the English Channel. Supporting them required continuous supply runs, LSTs shuttling back and forth, England to France to England, around the clock. Each trip exposed them to weather, to German submarines prowling the channel, to mines and aircraft and the simple mechanical stress of driving ships at full speed in hostile waters. The welded hulls held. 7 LSTs were lost during the Normandy campaign. LST 314 hit a mine off Sword Beach on June 7th. LST 496 took a direct hit from German artillery on June 9th and burned to the waterline. LST 523 sank after colliding with a cargo ship during a storm on June 18th. But in every case, the loss wasn't from welding failure. The ships had been destroyed by external violence, explosions, fire, collision, not internal structural collapse. The welded seams that the Navy had feared, that engineers had tested and retested, that represented the biggest gamble in American shipbuilding history, performed exactly as Joseph Scullion had predicted. They held. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The scope of the achievement became clear only in retrospect. Between December 1942 and June 1944, American shipyards had produced 1,051 LSTs. Richmond's yards, alone, had built 524, exactly half the total fleet. Every single one used skip welding as the primary construction method. If Scullion's technique had failed, if even 10% of those vessels had developed stress fractures, if welded seams had cracked under combat conditions, the invasion would have stalled. Not failed entirely, perhaps, but delayed, reorganized, pushed back into summer and then autumn. And delay in 1944 meant giving Germany time to complete the Atlantic Wall, time to move reinforcements, time to develop the jet aircraft and rocket weapons that were already in prototype stages. The Allies won the race against time by 11 months, from the authorization of skip welding in December 1942 to D-Day in June 1944. 18 months. Without that technique, without the 60% reduction in construction time that it enabled, the earliest possible invasion date would have been spring of 1945. History turns on such margins. But the human cost of the production miracle was rarely discussed in the official histories. Richmond's shipyards operated 24 hours a day, 7 days a week, for the entire duration of the war. Workers pulled 12-hour shifts, sometimes longer when production schedules demanded it. The yards employed 90,000 people at peak capacity: housewives, teenagers, elderly men past draft age. Anyone who could hold a tool or read a blueprint or follow instructions shouted over the constant thunder of industrial construction. They worked in conditions that would horrify modern safety inspectors. Welding flashed the ultraviolet radiation from welding arcs burned eyes and skin. Metal dust filled the air, settling in lungs, causing respiratory problems that wouldn't manifest until decades later. Industrial accidents were common: falls from scaffolding, burns, crushed limbs, electrocutions. The yards kept medical stations staffed around the clock, and the pace never relented. Every delay had consequences measured in lives. If a hull took an extra week to complete, that might mean an LST arriving late for an invasion, which might mean supplies running short on a beachhead, which might mean a battalion pinned down without ammunition or medical support. The connection between a welder's productivity in California and a soldier's survival in France was direct and visceral. Joseph Scullion felt that weight personally. After his technique was adopted, he became, in effect, a troubleshooter for the entire Richmond complex. When a welding crew encountered problems, Scullion was called in. When quality control rejected a section of hull, Scullion examined it. When new welders needed training, Scullion designed the curriculum. He worked 7 days a week from December 1942 through August 1943, when exhaustion finally forced a reckoning. On August 14th, during an inspection of hull 728, Scullion collapsed. Heat stroke, the doctors said. Combined with malnutrition, he had been skipping meals to stay on the production floor, and simple physical depletion. They ordered him to rest for 2 weeks. He was back in the yard after 4 days. The pressure came from everywhere. From Kaiser's management, which had promised Roosevelt specific production numbers, and now had to deliver them. From the military, which sent liaison officers to monitor progress and report any delays to Washington. From the workers themselves, who understood that their brothers, sons, husbands were waiting in England for the ships that would carry them to France, and from the knowledge that the enemy was watching, German intelligence tracked Allied shipbuilding capacity obsessively. Every delay, every production shortfall was noted, analysed, fed into strategic calculations. The Kriegsmarine knew about the LST construction program. They knew the approximate numbers. What they didn't know, what they couldn't have predicted, was that American shipyards had abandoned established doctrine in favour of an unproven technique. German naval architects still designed using rivets, their shipyards still employed traditional methods. When German intelligence estimated Allied production capacity, they based those estimates on riveting timelines. They predicted America might produce 500 LSTs by mid-1944. The actual number was more than double that. The margin of error in German intelligence, caused entirely by their failure to anticipate the skip welding revolution, was itself larger than Germany's entire amphibious warfare capacity. This is what defeat looks like in industrial warfare. Not dramatic battlefield reversals, but the slow accretion of miscalculation. Germany's strategic planning for 1944 assumed the Allies lacked the shipping to sustain a major invasion. That assumption was based on sound reasoning and accurate intelligence. It was wrong anyway, because the fundamental premise that ships had to be riveted had been overturned by a Pennsylvania welder looking at a warped hull plate on a cold November morning. The broader implications of skip welding extended beyond LSTs. By mid-1943, the technique was being applied to Liberty ships, the mass-produced cargo vessels that carried supplies across the Atlantic. Liberty ships had been plagued by welding failures since the program began. Several had literally broken in half at sea, validating every concern the Navy had about welded construction. But those failures came from continuous welding, from the thermal stress that Scullion's technique was designed to eliminate. When Liberty ships began incorporating skip welding in critical seams, the failure rate dropped dramatically. From January to December 1943, 18 Liberty ships were lost to structural failure. From January to December 1944, after skip welding became standard, the number dropped to 3. The technique spread further. Victory ships faster, more advanced cargo vessels designed to replace the Liberty ships were skip welded from the keel up. Destroyer escorts used it. Even fleet carriers began incorporating the method in non-critical structural elements, then gradually in more essential seams as confidence grew. By 1945, the United States Navy was the most comprehensively welded fleet in naval history. Every major combatant launched after mid-1943 used skip welding somewhere in its construction. The technique that had been forbidden by regulation in June 1942 was standard practice by June 1944. And yet Joseph Scullion's name appears in exactly 7 documents in the National Archives. 3 production reports from Richmond Yard 3. 2 training manuals that list him as a technical consultant. 1 payroll ledger. 1 commendation letter from Henry Kaiser, dated March 1943, praising the innovative workforce of our Richmond facilities, without naming anyone specifically. He received no military decoration, no presidential citation, no public recognition of any kind during the war. The technique he pioneered was classified as essential war production information, which meant discussing it publicly could result in prosecution under wartime security laws. Even after the war, the Navy's official histories mentioned skip welding only in technical appendices, described in the passive voice as a method that was developed during the early war period. Developed by whom? The histories don't say. This erasure was partly bureaucratic inertia, the military's institutional resistance to crediting individuals over organizations, but partly deliberate. Acknowledging that a civilian welder had overturned decades of naval engineering doctrine, that the Navy's own experts had been wrong about fundamental shipbuilding principles, would have been embarrassing. Easier to present the innovation as a collective achievement, a natural evolution of industrial practice, rather than the insight of one man questioning established wisdom. Scullion himself seemed content with obscurity. Letters he wrote to family members during the war preserved by his daughter, and later donated to the Rosie the Riveter National Historical Park archives, mention his work only in passing. He wrote about production quotas met, about training new workers, about the satisfaction of seeing hulls he had worked on being launched. But he never claimed credit for the technique, never expressed frustration at the lack of recognition. "Did my job," he wrote to his brother in July 1944, 2 weeks after D-Day. "Ships are in the water. The boys made it to the beach. That's all that matters." The pragmatism was typical of his generation. Men and women who had lived through the Depression, who understood scarcity and necessity in visceral ways, who approached the war not as an adventure, but as a problem requiring solution. Get the work done. Don't complicate it with ego or ambition. Measure success in outcomes, not recognition. But the absence of recognition created a historical problem. Without Scullion's name attached to the innovation, without a clear narrative of how skip welding was developed, the technique became just another line item in the vast catalogue of wartime industrial improvements. Historians writing about D-Day focused on strategy, on combat, on the famous names Eisenhower, Bradley, Montgomery. The ships that made the invasion possible were background detail. Even histories of industrial mobilization tended to gloss over the specifics. Henry Kaiser got credit for revolutionizing shipbuilding through mass production techniques. The workers got collective praise as the arsenal of democracy, but the actual technical innovations, the specific insights that transformed theory into practice, were lost in the general narrative of American industrial might. This matters because it distorts how we understand technological change. The standard story presents industrial progress as the inevitable result of throwing enough resources at a problem. America won because it had more factories, more workers, more steel. The implication is that victory was predetermined by material advantage. But that's not what happened. Material advantage meant nothing if the factories couldn't produce fast enough. America had abundant resources in 1941, yet was still projecting a 1945 invasion date in mid-1942. The resources were useless without the method to exploit them efficiently. Scullion's innovation didn't just speed up production, it changed what was possible. It transformed a strategic impossibility, invading France in 1944, into a difficult but achievable objective. The difference between impossible and difficult is everything in warfare, and it happened because one person looked at a warped hull plate and asked a simple question. What if we're doing this wrong? The final accounting came years later, long after the war had ended, long after the shipyards had gone quiet and the workers had dispersed back to civilian life. In 1952, the Navy's Bureau of Ships commissioned a comprehensive study of wartime construction methods, trying to understand what had worked, what had failed, and what lessons should be carried forward into the Cold War era. The study ran to 3,000 pages. It analyzed every major vessel class, every construction technique, every innovation implemented between 1941 and 1945. The section on welding methodology occupied 217 pages. Buried in Appendix 7, Paragraph 12, Subsection C, the study noted, segmented thermal application welding, commonly known as skip welding, reduced LST construction time by an average of 58% compared to traditional riveting methods. Structural failure rates were 4.3% lower than riveted construction. Technique was developed at Kaiser Richmond Yard 3 in late 1942. No names, no individual attribution, just a clinical assessment of efficiency gains. Joseph Scullion never read the report. By 1952, he was back in Pennsylvania, working for a steel fabrication company in Erie, welding water towers and bridge supports, the same work he had done before the war. He was 53 years old. His hands had developed a tremor, whether from decades of welding or from something else. The doctors couldn't say. He told friends it didn't matter. He could still work. He worked until 1964, when the tremor became too severe to hold a torch steady. Retirement found him restless. He took consulting jobs, taught welding at a community college for 2 years, and spent time with his grandchildren. When people asked about the war, he told stories about Richmond, about the workers he'd trained, the hulls he'd inspected, the frantic pace of production. He mentioned the technique once or twice, but never dwelled on it. A lot of smart people figured out a lot of things back then, he told an interviewer from the local historical society in 1966. I had one idea that worked out, probably saved some time, but the real heroes were the boys who rowed those ships to the beach. He died on March 7, 1967, of congestive heart failure. The obituary in the Erie Daily Times was 4 sentences long. It identified him as a retired welder, a veteran of industrial war work, survived by his wife Mary, 3 children, and 7 grandchildren. Services were held at St. Patrick's Church, burial at Laurel Hill Cemetery. No mention of LSTs, no mention of D-Day, no mention of the technique that had enabled the greatest amphibious invasion in history. The erasure continued for decades. Histories of World War, 2 devoted chapters to aircraft production, tank development, radar technology, the Manhattan Project. Shipbuilding received cursory treatment, usually a paragraph about Liberty ships and Kaiser's assembly line methods. The technical details were considered too specialized, too mundane for general audiences. This began to change in the 1980s, when historians started focusing on the industrial and technological dimensions of the war. Books appeared analyzing production methods, examining how America's industrial capacity was mobilized and organized. The LST construction program received more attention, recognized as a critical enabling technology for Allied strategy. But even these more detailed histories struggled with attribution. Who had developed skip welding? The paper trail led back to Kaiser's organization, to engineering department memos and production reports that documented the technique's adoption, but not its origin. Some historians credited Kaiser himself as the driving force behind shipbuilding innovation. Others attributed it to anonymous engineers or to the collective ingenuity of the Richmond workforce. The truth emerged slowly, pieced together from scattered sources. A researcher at the Rosie the Riveter National Historical Park, going through donated documents, found Joseph Scullion's personnel file from Richmond Yard 3. The file contained his original proposal to Dutch Hendricks, dated November 1942, describing the skip welding technique in technical detail. Cross-referencing that document with production records, training manuals, and testimony from surviving shipyard workers, the researcher, a graduate student named Patricia Hernandez, working on a dissertation about wartime industrial innovation, was able to trace the development and adoption of the technique. Her dissertation, completed in 1993, was the first academic work to identify Scullion by name as the technique's originator. The dissertation itself received little attention outside academic circles. It was published by a university press in an edition of 800 copies, most of which went to libraries, but it established the documentary foundation for future research. When the National World War II Museum in New Orleans began developing exhibits about industrial mobilization in the late 1990s, Hernandez's work provided the sourcing they needed. In 2004, the museum opened an exhibit titled The Arsenal of Democracy, Industrial Innovation in World War II. One section focused on shipbuilding. Among the displays was a reproduction of Scullion's original proposal document, alongside photographs of Richmond Yard 3, samples of skip-welded seams, and a timeline showing how the technique spread through American shipyards. A small placard identified Joseph Scullion, included a brief biography, and noted, his innovation reduced LST construction time by nearly 60%, enabling the D-Day invasion to proceed on schedule. Scullion's daughter, Margaret, attended the exhibit opening. She was 71 years old and had brought her own grandchildren, Scullion's great-grandchildren, to see the display. A museum curator asked her what she remembered about her father's war work. He never talked about it much, she said. I knew he worked in the shipyards. I knew it was important, but he never made it sound like he'd done anything special. Just his job, he'd say. Just doing what needed to be done. The curator pressed gently. Has he ever mentioned the welding technique? The impact it had? Margaret thought for a moment. Once, she said. This would have been in the 60s sometime. There was something on television about D-Day, one of those anniversary specials. They were showing the landing craft hitting the beaches, and Dad was watching, and he said, "I remember this exactly," he said. "I welded some of those. Not that he'd invented anything, not that. He'd changed how they were built. Just that he'd welded them. It was the same as welding a water tower." This modesty, this self-effacing refusal to claim credit, was characteristic not just of Scullion, but of his entire generation of war workers. The women who built bombers, the men who cast artillery shells, the teenagers who assembled radio equipment. They understood their work as essential but not exceptional. They had done what the war required, no more, no less. But this modesty creates an obligation for those who come after. If the people who changed history won't claim credit, then history must claim them. Their names must be remembered. Their innovations must be understood not as inevitable technological progress, but as the result of specific human insight, specific moments when someone looked at an impossible problem and refused to accept the impossibility. The numbers tell part of the story. 1,051 LSTs built between 1942 and 1945, 524 from Richmond alone, 236 at Normandy on June 6, 1944, 157 in Sicily, 108 at Salerno, dozens more at Anzio, in southern France, at Pacific Islands whose names became synonyms for brutal combat, Tarawa, Saipan, Iwo Jima, Okinawa. Each invasion depended on the ships getting there. Each ship depended on the welds holding. Each weld traced back, through production chains and training programs and quality control procedures, to a technique developed by a Pennsylvania welder who thought the Navy was building ships wrong. But numbers alone don't capture the human dimension. Consider LST 327, which hit Utah Beach at 6:30 on the morning of June 6th. The ship carried Company B of the 1st Engineer Special Brigade men, whose job was to clear beach obstacles under fire, to blast paths through minefields, to make the beach passable for the infantry following behind them. The ship's commander was Lieutenant J.G. Thomas Ellsworth, 23 years old, from Iowa. He had never commanded a ship before, had received abbreviated officer training because the Navy needed LST crews faster than they could train them properly. His knowledge of naval architecture was minimal. He knew his ship was welded, knew there had been some controversy about that, but the details meant nothing to him. What mattered was getting his cargo to the beach. He drove LST 327 through heavy seas, the storm that nearly forced Eisenhower to postpone the invasion at full speed, the flat bottom pounding against waves, the entire hull shuddering with each impact. Engineering calculations suggested this kind of stress could cause welded seams to fracture. Ellsworth didn't know that. He knew only that men were depending on him to arrive on time. LST 327 beached at exactly 6:30, precisely when the invasion plan said it should. Company B rushed out into water that was deeper than expected, into machine gun fire that was heavier than expected, into a beach that was more heavily defended than intelligence had suggested. 43 men from Company B died that day, but 117 survived, and they cleared a 400-yard section of beach, and the infantry that came behind them had a path inland, and the invasion continued. LST 327 made 7 more trips to the beach that day. Each time, German artillery tried to sink it. Shells hit the water nearby, close enough that shrapnel tore holes in the superstructure, close enough that concussion waves rang through the hull like hammer blows. And each time, Lieutenant Ellsworth waited for the sound of metal tearing, for the rush of water that would mean his ship was dying. It never came. The welds held. Ellsworth survived the war, returned to Iowa, became a high school teacher. In his classroom, he kept a photograph of LST 327. When students asked about it, he told them about D-Day, about the men he'd carried to the beach, about the importance of doing your job even when you were terrified. He never mentioned the welds. Why would he? They had done what welds were supposed to do. They had held the ship together. It wasn't dramatic. It wasn't heroic. It was just engineering working as engineering should. But that's precisely the point. The heroism wasn't in the welds holding it, was in the decision, 18 months earlier, to trust a new technique. To gamble men's lives on the intuition of a Pennsylvania welder who thought he had a better way. That gamble was made by Dutch Hendricks, who approved Scullion's initial experiment, by Henry Kaiser, who took the results to Washington, by the War Production Board officials who overrode Navy regulations, by the quality control inspectors who certified welds they'd been trained to reject, by the thousands of welders who learned the new technique and applied it with precision despite the pressure of impossible production schedules. The gamble paid off. But it could have failed. If skip welding had proven unreliable, if even a small percentage of LSTs had developed stress fractures, the consequences would have cascaded through the entire invasion plan. Delays would have compounded. Schedules would have collapsed. The window for invasion might have closed entirely. Instead, the technique worked better than anyone had anticipated. Post-war analysis showed that skip-welded seams were not just faster to produce but actually superior to riveted construction in most stress conditions. The method that had been adopted out of desperate necessity turned out to be objectively better engineering. This pattern repeated throughout the war. Innovations developed under extreme time-pressure radar, the proximity fuse, improved aircraft engines. Synthetic rubber often proved superior to the established technologies they replaced. Necessity didn't just drive invention. It forced a willingness to question fundamental assumptions, to experiment with untested methods, to accept risk in pursuit of improvement. The peacetime world is more cautious. Regulations accumulate. Standards become rigid. The bureaucratic impulse is to avoid risk, to stick with proven methods, to prioritize safety over innovation. These impulses are not wrong. They prevent disasters. They protect people from the consequences of reckless experimentation, but they also prevent the kind of breakthrough that Joseph Scullion achieved. His technique would never have been adopted in peacetime. The Navy would have tested it for years, demanded extensive peer review, and required proof of reliability that could only come from long-term observation. By the time skip welding was officially approved, the war would have been over. Crisis creates permission for innovation. The question is whether innovation requires crisis, or whether societies can find ways to maintain that willingness to question, to experiment, to trust individual insight over institutional inertia, even in the absence of existential threat. The LST construction program suggests an answer. The technique itself, skip welding, was not complicated. Any competent welder could learn it in a few days. The insight that made it possible was not arcane technical knowledge, but simple observation. Metal warps when heated continuously, so don't heat it continuously. The obstacle wasn't technical, it was institutional. The Navy's regulations, backed by decades of experience and legitimate concern for safety, had calcified into doctrine. Questioning that doctrine required not just insight but authority, the authority of crisis, which made caution more dangerous than risk. Joseph Scullion had the insight, but it took Dutch Hendricks's willingness to listen, Henry Kaiser's willingness to advocate, and the War Production Board's willingness to override the Navy for that insight to become policy. Innovation required not just the innovator, but an entire system willing to amplify rather than suppress unconventional thinking. That system didn't survive the war. The Navy returned to traditional procedures. Regulations that had been waived in emergency were reinstated. The rapid pace of wartime innovation, the willingness to test new methods, to adopt successful techniques immediately, to prioritize results over protocol, gave way to peacetime caution. This was probably necessary. Wars end. The crisis mindset that enables rapid innovation also creates corners cut, safety compromised, long-term consequences deferred. A society can't operate indefinitely in emergency mode without exhausting itself. But something was lost in the transition. The men and women who had improvised solutions to impossible problems, who had questioned established wisdom and been proven right, mostly returned to conventional careers. Their insights were documented in technical reports that few people read. Their names disappeared from the historical record. Joseph Scullion went back to welding water towers. The technique he pioneered became standard practice, taught in engineering schools, used in shipyards worldwide. But divorced from his name, from the specific story of how and why it was developed, Skip welding became just another technical procedure. Students learned the method without learning the lesson, that established doctrine can be wrong, that individual insight matters, that the difference between impossible and achievable can be a single person willing to question assumptions. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.